Okay, so on number 3, section 5.1 review, page 163, a worker pushes a 1.50 times 10 to the third Newton crate with a horizontal force of 345 newtons, a distance of 24 meters. Assume the coefficient of kinetic friction between the crate and the floor is 0.220. As I said yesterday, I really recommend you guys draw a free body diagram. All the forces acting on the crate. We got weight. We got normal force from the ground. Applied force. Well, that's the worker pushing it. You could put F subscript W for worker.
That's friction.
And then friction. Okay. And that's kinetic friction, right? Because it's moving.
Mm-hmm.
Okay. All right. Now, remember what work is. Work is force acting over a distance. And when we describe work, we can do it in different ways, and that's what number 3 is doing. We can talk about the work done on the crate by the worker, or the work done on the crate by friction, or the work done on the crate by gravity, or even the work done on the crate by the earth, which will be the normal force, right? So we can isolate them. Then we can talk about the total work or the net work done. And that would be where we combine all, where we can combine all of them, right? So that's what number 3 is asking us to do. Okay, we started on A yesterday, but the bell was ringing and I was like, ooh. So let's just, so let's just back up from the beginning. How much work is done by the worker on the crate? So the work done by the worker, I'm going to put a subscript W, because that might, if we change applied to W for worker, maybe that'll help. So that's what? That is the force applied by the worker times the distance times the cosine of the angle between the force and the distance. Okay, so what was the work, or what was the force applied by the worker? 345? And what distance did it move? 24 meters? Okay, and if we just say, it's the worker's pushing the crate, right? So the distance is in what direction? And the force of the worker is in what direction? Right? Newton's second law? Okay, so we know, even though they didn't spell it out for us, the distance is in this direction. Okay, good. So if you got distance in this direction and the force of the worker in the same direction, the angle between them would be, good Alyssa, zip. And cosine of zip is 1, yay. So we multiply these together.
8,280.
Get it. Okay. Do we need a round for sig figs?
We have 3.
I don't know.
No, we have 3.
We have 3.
Oh, I have a headache. That's all.
We have,
Don't pay attention to the look on my face right now. I really do. I need headache meds.
It looks pretty.
I think you, but I don't know. I feel weird. Huh?
I think so.
Okay.
I feel like something bad got
We're recording. Just so y'all know, we are recording right now, and it's going to be on YouTube this evening.
Ah,
Well, how many subscribers do you have?
I don't know, but here, let's,
Okay.
okay. All right,
10.
these measurements have how many sig figs each? That's 345 has 3 sig figs, 24.0, 3 sig figs, so this should be,
3.
is it?
Yeah.
Yep, we're good. What's the unit?
Joules.
1. Okay, good. What's the definition of a joule? A newton times a meter. Good. Yay. You're done with part A.
Yay.
Okay.
Now the 2 other parts.
All right. 2 other parts. Okay. Part B. Okay, on part B, how much work is done by the floor on the crate? Okay, let's go back to the, okay. Does everybody agree? We're talking about friction.
Yeah.
Okay. So, the work done by friction is the force, and we put it over here as F sub K, right? Okay. Distance, cosine of the angle between them. All right. So what is the force of friction?
I'll get in between what?
In between the force, okay. It's the angle between the force and the distance the object moves.
It gives you the coefficient of the kinetic friction.
Yeah, let me finish this thought real quick. Hold on a second, Nick. Chance, here's the demo. I think you missed that day. Flip your book. In what direction was the force? In what direction was the distance moved? Okay, you got up and up. What's the angle between them? 0. See what I mean?
0 is 1.
Okay, Nick, we got what? Coefficient of?
Coefficient of kinetic friction.
Okay, so instead of this F sub K, we'll put in the formula for friction. How do we find friction? Coefficient times?
Times gravity? No.
Normal force. Coefficient of friction times normal force. Then times D, cosine of the angle between them. All right, how are we know that, we can get that. How are we going to find the normal force? Let's go back to our diagram. A picture's worth 1,000 words.
So, it's equal to gravity.
Right, because it's not on an incline. Yeah, here.
9.8
This is not on an incline.
It's equal to the weight of
So, yes. Therefore, say it again, Nick.
It's equal to the weight of the box.
Normal force is equal to the weight of the box. Because it's not on an incline, we have no components. This and this are equal and opposite each other. Is the box going here vertically?
No.
I've been doing that all day, y'all. I look like a fool up here, but it gets their attention. Okay. That's why I try to calm down during AP and during physics. Because the rest of the day I'm just like, whoa! Am I lying? That might be why I have a headache.
Maybe.
Okay.
I think
Do y'all see that? If the worker were pushing this up an incline, well then gravity would be in components, right? And that's the mess that you've been dealing with.
a mess.
But now we're back to the nice, neat stuff that you had
Yay.
before the mess that you may have forgotten,
Good.
which some have. There's no incline. There's no components to weight.
That means weight is weight.
All of weight is balancing normal force.
Yes.
Yay.
Yay.
So how do we calculate weight?
But it gives you the weight of the crate. Weight.
Oh, they do. Nice.
So it gives you the, scientific notation of the
But it's still,
crate.
okay, but it's still weight, isn't it?
It's in newtons.
Isn't all forces in newtons? Weight is the force of gravity pulling on the mass.
Okay.
So we're good,
All right.
right? Yay, we don't have to calculate anymore. Or derive, rather, I'm sorry. Okay, so what's the coefficient of friction?
0.220.
Okay, what's the weight?
1.50 times 10 to the third newtons.
And the distance was 24
Yes,
meters?
24 meters. 24 meters.
All right. Now, in what look at the diagram again. In what direction is the distance?
Positive.
Positive. In what direction is friction?
Negative.
Opposite. Chance, look up here. Distance is going this way. Friction's going that way.
180 degrees.
It's a 180-degree angle. Do you see that?
It's a straight line.
Okay, so cosine of 180. Cosine of 180 is what?
0, 1.
Negative 1.
I couldn't get there.
Negative 1.
I never had a cosine of what you taught me, so. It's not here. I dropped that out too. I didn't drop out. Miss Buffy gave us A's.
Ace man. It's not
Okay.
your shit though.
We're recording.
Thanks for the motion.
Okay. Okay, well,
How many people look at your YouTube?
huh?
How many people look at your YouTube? You can check that out.
Okay, all right, well, I'm sorry for that, but you're welcome. I'll help you
thank
any
you.
way I can.
Thank you.
Okay. Okay, so, punch all that in the calculator.
Wait.
It should be negative, yes.
Yeah.
Because remember, friction does negative work. Remember that from when we, Monday? You don't? You weren't here. Alyssa, push on your book, across the table. Okay. You did work on the book, and friction did work on the book. You did positive work because your force is in the same direction as the distance moved. But friction is always opposite motion. So if friction is opposite motion, that means it's doing negative work. Are you okay with that? And then the cosine 180 proves it mathematically. Okay. Y'all got a number yet? Okay. Give me a number. All of it off the screen.
Negative 7,920.
Is that exactly what it
That's
says?
exactly what it says.
Okay. How we doing on sig figs?
Good. Not. Yes. Yes. It's because we know that's.
Okay. We good?
Yeah.
Okay. Good. And it would be joules. Yay.
That's almost as much as the force of the worker. Because he did 8,000, and this dude did almost, the person
Almost
did almost 8,000, yeah.
Interesting. And we're about to get to that.
Oh.
Isn't it? Very cool.
I love how you just drew like, all the way down.
I know. I need to calibrate this thing.
Sadie's gonna be watching like, what?
Okay, part C. What is the net work done on the crate? And no, it's not CNN. Is that what you were grinning about? I hate saying that because that's what I think of too. All right.
They're about to come in.
Huh?
Our recycling children are about to come in.
Y'all gonna scare them? Okay.
Yell at me
Well, just remember we're recording. Okay, so how are we gonna find the net force? Oh, wait. Can I tell you an easier way to do this?
Yes, you can. I guess.
I mean, I ain't gonna say no.
Net anything is what?
Addition of all of it.
Addition of all of it. Good, Alyssa. The sum of all the work acting on it.
What is that?
What are you doing?
That's the Greek letter sigma. It means sum.
So according to quantum theory, the radius of the sun.
I don't think they pay attention.
Okay, so what all work are we dealing with here?
All of it.
All of it, because,
Well, the natural force of gravity cancels, so we're just dealing with the worker and the friction.
right,
It's that right letter.
excuse me?
It's that right letter.
So it's just the difference between A and B.
360 joules.
Okay, so we got the work done by the worker was what? 8280?
Minus 7,200, or 7,920.
And why is it minus, Nick?
Because that's a negative.
Yeah, it's negative work, right?
I said the difference, and she's like, no, it's adding,
You're adding a positive work to a negative work.
which would be the difference between those two.
What is it?
360.
Yes.
Add a decimal after it for sig figs.
Because it's got to end in the ones place, right? Okay, we rarely deal with addition and subtraction on sig figs.
Yeah, your unit.
Yeah. Thank you, Donna. When you add or subtract, you're not looking at total sig figs, you're looking at the decimal place of the least precise measurement, right? Both of these end in the ones place, so this has to end in the ones place, so that's why we stick the decimal there, okay? Unit is joules. So positive work was done. Not much,
That's why I
but
moved in that direction.
that's why we're in that direction. Okay, so that's number 3.
It also explains why it's hard to push a heavy object.
Yes.
More weight has more friction.
More friction, because the more weight, the more normal force, right?
Mhm.
Okay. Now, the rest of this assignment is due tomorrow.
Well, it's supposed to be.
So please have that in tomorrow. I will give you a little time at the end of the period to continue working on it. But for right now, y'all look at page 164. The rest of the stuff we're going to deal with in this unit, we just dealt with work. Now we're going to deal with energy. Okay.
Ooh.
We're going to be exploring kinetic energy, potential energy. There are 2 types, gravitational and elastic.
GPE.
And then we're going to compare the differences between mechanical energy and non-mechanical energy. And that's where you get a distinction between chemistry and physics, usually is that. Then power. And then we'll be done with this unit.
And the other day when we were watching that Tony Hawk video, those kids walked in here, and later on the bus, that it was, you know, watch it. I was like, probably the oldest show ever, had Tony Hawk in it.
It was literally 30 whenever it was taped, because he's 47 now. I Googled it while we were watching.
Oh, really? Yeah, it's old.
He's like, how old was he during that? He's like, he must have been like 19. I was like, oh, man, he was quite a bit older than that.
So he's almost my age.
Yeah, he's
So is my
47.
parents.
Okay, just
So
bunch
is
of
my
mine.
parents.
Your parents?
Well, I joked and was like, I bet it's like 30, and then I Googled it, and he probably was like 30 when that was done.
Good call.
Uh,
Okay, now, kinetic energy. What is it? We know.
the energy kinetics.
That it's the energy when it's moving.
Yeah. Give something some kinetic energy.
I almost did my calculator.
Something that won't break the bank. Okay. All right, so what did you do? You set it in motion. You set it in motion.
The energy of object.
Yeah, I know, Shelley says. Same stuff in chemistry.
Right.
It's freezing in here. I'm just
I'm
throwing
running
that out there.
No, it's hot in here. I don't know what it is.
Okay.
Always hot.
All right, so
Wake up.
kinetic energy is the energy of motion. Anything, your pencil, your jacket, your book, your car, your bicycle, your hoverboard, you.
Oh, I said at the same time.
Jinx, you owe me a coat.
I'm dying.
Diet. No, I'm teasing. I actually probably owe you a coat. Okay. So y'all, and even molecules have kinetic energy because they're doing this. We can't see it,
It's shaking.
but they're doing that, right?
Yeah.
In this table, they're doing this. In the air, they're doing that, right? I know. I don't even think about it because I can't. You know how foolish I look up here.
Good thing it doesn't video you.
I know, but I'm supposed to, here very soon, I gotta get a camera and record the whole classroom for national board.
They're gonna be like,
Chance, no more
"Ooh, lady,
sleeping.
Friday.
Yeah, Chance, no more sleeping.
You can't do that.
it."
Have a hat. Hat.
All right.
No, so Chance.
So good. We understand kinetic energy qualitatively. Mathematically, quantitatively, it's 1/2 mass times velocity squared. You saw that in the video. The unit, well, it's the energy unit, joules. Work is a transfer of energy. You lift your book, the book now has more energy. Well, how did it get that more energy?
You.
From you transferred it from your muscles to the book.
And you got the energy from the muscles from the food you ate, which you got it. And the chicken got it from the seeds that say we got it from the sun.
Right.
Oh, yeah.
Which got it.
So ultimately, all energy on this planet comes from the sun.
Which technically means that go green means go nuclear. Because the sun is nuclear.
Nuclear, right. And at the end of the period, Bryce showed me a really wild website. They suspect that the hydrogen at the core of the sun is metallic. You know.
Dang.
Yeah, we'll look at it after this is done. Okay, so this is pretty straightforward. It's real easy. The only thing that catches me is that a lot of times I'll forget to square the speed.
Well, if it catches you.
What do you do?
Well, that's why I'm telling you, you gotta watch out for it, okay? But this stuff is easy, y'all. This is so easy. All right, take a look at 165. A 7-kilogram bowling ball. A 7-kilogram bowling ball moves at 3 meters per second. That is velocity. How fast? How fast?
So we're looking for.
We're looking for. What are we looking for? How fast?
So,
We're looking for velocity
We're looking for a velocity.
But there's already velocity.
Okay, so let's keep reading.
of a 2.45 gram table tennis ball. 4 or 5.
Okay.
I might have said 5 or I mean 4 5.
How fast must a 2.45 gram table tennis ball move in order to have the same kinetic energy as the bowling ball? And is this reasonable when you play? Okay, so we've got to find out some stuff, right? This is bowling ball, so I'm going to call that mass subscript B, velocity subscript B, velocity subscript T, mass subscript T. Are good with that?
We're good.
Chance? It says we want the table tennis ball to have the same kinetic energy as the bowling ball, right? So that means KE of the bowling ball equals KE of
Tennis ball.
the table tennis ball, right? Okay, let's substitute in some values. What's the equation for kinetic energy? 1.5. All right, so KE, so this is bowling ball, so that means the mass of the bowling ball.
Velocity v.
Okay, if you are not real comfortable with algebra, heads up. Okay? It's not hard, but you gotta pay attention. It's tedious. Okay, but not conceptually difficult.
Velocity subscript
Okay.
v.
Velocity subscript B, because it's the velocity of the ball. We're dealing with the bowling ball on the left side, right?
Squared
And that's gotta be squared.
equals
1/2 mass of table tennis ball, velocity of the table tennis ball squared. What is our unknown?
Velocity of the table tennis ball.
Right. So we need to isolate that.
So 2 times it by 2 on that side gets rid of the 1/2. So just
Yeah.
divide by
No.
mass of the table tennis ball.
Pause for a second. Got to get engaged. All right. This is where a fork in the road happens. If you are comfortable with rearranging without sticking in numbers, follow me. If you are not, you need to go ahead and start sticking in numbers now on your paper and start solving. Okay? All right. All right. We've got to get everything but that on one side, right? Okay. So let's take it step by step slowly,
Okay.
because Sadie's watching tonight. Okay, so what's the first thing we're going to do?
Move the 1/2 on
Okay.
the table tennis side to the outside.
So if we multiply by 2, right?
Yeah.
So we're going to multiply this by 2, right?
And that gets rid of that.
And that gets rid of that. That's nice. Okay, now what?
Divide by mass of the table tennis ball.
That gets rid of that. So we got to divide that by that, right?
And now you just have to square root the whole thing.
Right. We got to get rid of that. How do you get rid of square?
Square root.
Square root. You get rid of square with square root. So we're going to square root this. So we got to square root that. Okay, Melissa?
Oh, so the mass of the bottom one is in grams and the top one is in kilograms. Are we fixing?
We're going to have to do a conversion.
Okay.
Good eye. Good eye.
So that just gets rid of the 2 on that side, and we're left with velocity of the table tennis ball on that side.
Okay, so yeah, let's clean this up. Velocity of the table tennis ball is square root of mass of the bowling ball, velocity of the bowling ball squared.
Yeah.
Yeah, okay. Over mass of the table tennis ball. Agreed? Do you want to check units before we continue? It would be wise. Okay. Let's just check these units before we go any further. Okay. That's, and yes, let's address that right now. Alyssa caught that we've got 2 different mass units. We got to get rid of them. Velocity has no mass unit, right? Okay, so which one do we want to get rid of? Grams. Yeah, in physics, we always deal with kilograms, right? We always deal with kilograms in physics. So let's get this changed to kilograms. 1,000 grams in a kilogram. So that would be what? 0.00245?
Yeah.
Thank you for that, Alyssa. Good job. Okay, all right, so let's check our units. We've got it right here, so let's just do it over here. Okay, so this is gonna be what, kilograms times, when you square velocity, that's gonna be what, meters per second, quantity squared, that's gonna be meters squared over seconds squared over what, kilogram, and you're taking square root, right?
That's just K.
Okay, so that cancels. So you end up with square root of meters squared over seconds squared. So what's that gonna be?
Meters per second.
And that's velocity, so we're good. Our equation is good. So let's plug it in. Okay, so the bowling ball was 7. Velocity of the bowling ball was 3. Table tennis, 0.00245 kilograms. I should not be the only one touching the calculator.
$8,571. Oh, wait, never mind. I did it wrong.
Sig figs, 3. Okay, so we need a decimal there, right? Yeah, everything in here's got 3 sig figs. So 160 meters per second, we already established that. Okay, we're not done yet. If you did not get 160, practice the calculator. Okay? If you need to, do little steps. Okay? I do that. There's no shame in it. I don't do it all in one fell swoop on the calculator. Okay? You're not going to have any AP exam to worry about with timing, so it's good. In college, they're timed. Sorry, I mean, those professors will not let you come back later to finish a test, and they will not extend it to another class period. It's that one class period, when at the end of the period, you hand in your test, that's done. That's it, okay? Just fair warning. We gotta start getting y'all this semester here to that.
Okay, teachers, you can get back on track now.
Okay,
Thank you.
so the other part of the question says, is this reasonable when you play table tennis?
No.
I wouldn't think so. Good God, 160 meters per second, boom. Right? Right? Because
I like how that one's only going.
160 of these in a second.
And the
That ball would put a hole through us, wouldn't it? So we need to say,
the volleyball's only going on 3 meters a second. So it would just be like,
yeah,
and you're like,
no, not reasonable
if someone threw a volleyball at you really hard,
speed
that would be the equivalent.
for play. Now you're done.
Someone had a bowling ball.
Okay, that's very interesting. That is very interesting. Why? The bowling ball's just going 3 meters per second.
It's so decently fast.
Yeah.
You still hit your toe on the elbow.
Right, but why does the table tennis ball have to go so much faster?
Because the mass is smaller.
It's
Like when
lighter.
Mr. Crow comes in here and said, he said if a bee comes head on to a freight train, what would it take to knock the freight train off the track or something like that? It was like a couple trillion meters per second.
And that'll play into a topic we'll get to soon called momentum. Yeah.
Like how he was just like,
That day
if
was,
a bee hit a train,
I was like, what kind of train? Like a tool train? No, like a freight train.
and I was like, theoretically, yes, it would stop it.
Yeah. I was like,
But it would just
Like